Hi, everyone. So today we are going to go over our section 2.3, which is solving a formula for a specific variable. The objectives are as follows. We'll be able to solve a formula for a specific variable. And then the second objective, we'll be able to use the Pythagorean theorem. So Pythagorean theorem, our whole a squared plus b squared equals c squared, that's really looking at it from the one dimension perspective. So you want to think our right triangles, whereas from the two-dimension perspective, where we're on an x and y coordinate plane, we have our Pythagorean theorem converted into our distance formula, which is literally Pythagorean theorem, a squared plus b squared equals c squared in disguise. Again, one dimension, just think of lengths, number line. Whereas two dimension, you have a coordinate plane, an x-axis and a y-axis. Right, so let's jump into that first objective, and we have some notes here. I'll read it for you guys. We have all probably worked with some geometric formula in our study of mathematics. Formulas in general in math are really, really important. They help us sort of turn a real life problem into some structured situation so that we can arrive at a solution quite easily. And so when we get to this second objective, being able to solve a formula for a specific variable, all we're doing is once we have this formula represented, we just take the numerical value and substitute it in for the variable that we choose it to be. So we'll be practicing a lot of concrete examples in this section. We'll also be looking at formulas with various or a bunch of different variables in the formula, and we are specifically asked to solve for one of those variables. And so the key in those particular examples is to isolate the variable that they're asking you to isolate. But let me talk a little bit less so we can jump into our first example for today. We're asked to solve the formula v is equal to 1/3 pi r squared times h for h. So what is this specifically asking us for? We are just simply asking to isolate that h variable. So when we're looking at b is equal to 1/3 pi r squared times h, we just want to get h all alone on one side of the equation. So how do we do this? Let's go ahead and utilize our inverse operations. We are going to multiply both sides by 3. And now we're looking at 3v is equal to pi r squared times h. And then we are going to once again utilize our inverse operations and divide both sides by pi r squared. That way we have h all alone on one side. And so h is equal to 3v all over pi r squared. And we are done. Easy enough. So another little comments section. We have in the sciences, we often need to change temperature from Fahrenheit to Celsius or vice versa. Whether you're traveling to a different country and you see Celsius everywhere, but you're familiar with Fahrenheit and you need to do that conversion in your head, or let's say you grew up over in Europe, for example, and you came to visit the States, and you need to convert from Celsius to Fahrenheit because you see Fahrenheit everywhere. Well, in these next concrete examples, we will be practicing the conversion from Fahrenheit to Celsius and vice versa. So let's take a look at example 2. So we have C is equal to 5/9 in parentheses F minus 32. And what are we solving for? We're solving for our Fahrenheit, aka we need to get that F all by itself on one side of the equal sign. So let's utilize our inverse operations. Everything in the parentheses is being multiplied by that 5/9. So what we're going to do is we're going to divide both sides by 5/9. And so on that left-hand side, C, aka our Celsius, as a fraction is just C over 1. That way we can now utilize our whole keep, change, flip. We keep that first fraction the same. We change this division to multiplication, and then we flip that 5/9 to become 9/5. So when we end up multiplying straight across, we get 9C in our numerator all over 5. And this is equal to F minus 32. So we're almost done. The last step that we need to do is we need to add 32 to both sides. So our final value is our F is equal to 9C over 5 plus 32. This means that if you traveled to the States and you're very familiar with Celsius, all you would have to do is plug in your Celsius value into this formula. 9 fits C plus 32. And then you can convert it to Fahrenheit to gauge what the Fahrenheit is. And actually, I think this would actually work out better if you were from the States and you were traveling to an area that deals with Celsius. So if I was going to London, for example, or Sweden, then I saw up on the Megatron in the center city that it was 14 degrees Celsius. I plugged that in here. Divide that by 5, multiply it by 9, add 32, and then I get a sense of, oh, okay, that's really cold. All right. And then vice versa, if you were traveling to the States and you were familiar with Celsius, you would just want to plug it into this top equation. All right. Let's do another example together. So we want to isolate our H now. And we're given S is equal to 2 pi r squared plus 2 pi r h. And straight off the bat, that right-hand side, you can pull out a greatest common factor between those two terms. You can pull out a 2 pi r. And when you do, you're left with just r plus h in parentheses. That way, we can divide both sides by our 2 pi r very efficiently. And so we're left with S over 2 pi r is equal to r plus h. We're almost done. Our very last step is we need to subtract both sides by r. And so when we do that, we get our final result to be S over 2 pi r minus r is equal to our h. And if you wanted to write it so that the h was first, you can most certainly do that. Put in both scenarios. And there we have it. We are all done. Another little notes section. So sometimes we might be given equations that we solve it for y, or is solved for y and we need to solve it for x, or it's solved for x and we need to solve it for y. So in this next example, we're given an equation that has both x and y, and we're asked to solve it for y, aka we are isolating that y variable, putting y all by itself on one side of the equal sign. So we're given 8x plus 7y is equal to 15. We want to isolate that y, utilize our inverse operations by subtracting 8x from both sides. So now we're just looking at 7y is equal to 15 minus 8x. And we have one last step. Opposite of multiplication is division. So we're going to divide both sides by 7. And then our final result is just 15 minus 8x all over 7, and we are done. Right. Pretty straightforward. If you think I'm going a little too fast, feel free to pause. You can go back and rewind. This video is for you guys to use at your disposal. All right. So our second objective for today is being able to use the Pythagorean theorem, our famous a squared plus b squared is equal to c squared. And so anytime you think Pythagorean theorem, the first thing that should pop into your head is the fact that we have a right triangle. All right triangles contain a right angle, which measures 90 degrees. And then it's also important to denote the sides of our right triangle. So we have a nice, beautiful demonstration or illustration below over here. The hypotenuse of a right triangle is simply the diagonal of any right triangle in the world, aka it's the longest side. It's always going to be opposite that 90-degree angle. Whereas those two other sides of the right triangle are known as our legs. Our legs are interchangeable. And so from the ABC perspective, our C value always represents our hypotenuse, which is why I color-coded that in pink. And then our A and B are our green and blue values, but we can switch these and it will not change the result of our formula. B squared plus A squared equals C squared is the same as A squared plus B squared equals C squared. And so this next slide, I already have some notes written up, but it's just the short derivation of showing how our one-dimensional Pythagorean theorem can be converted into two-dimensional form, representing points on a coordinate plane. And so what I did was I just drew in one of our famous Pythagorean triples, a 3, 4, 5 triangle. How did I know that this was length 3? Well, if my y value maintains the same throughout both coordinates, that means we're dealing with a horizontal line. So we're in the one-dimensional world, and we just have to count how many spaces we're looking at. We start at 2, and then we end at 5. So we're at 1, 2, 3 units, aka our length is 3. The same exact concept applies when we're looking for our b value, except instead of it being a horizontal line, it is vertical. So we are once again in that one-dimensional world. Our x values are the same. So we just look at our y's and we take the difference. 6 minus 2 is 4, or we can count it 1, 2, 3, 4. So our b value is of length 4. Now that we have these one-dimensional lengths, we can plug them into our good old Pythagorean theorem, a squared plus b squared equals c squared, to find the length of this diagonal. 3 squared is 9, 4 squared is 16. Add the two together, you get 25. Last but not least, take the square root of 25, and you end up with your C value being of length 5. 3, 4, 5, Pythagorean triple. Now, how do we convert this into our two-dimensional world? Well, our a squared is the difference between our two different x values, 5 minus 2, which gives us this length 3, and then we square it. Our b squared is the difference between our two y values, 6 minus 2, in parentheses, squared. And then in order to get our diagonal, we need to sum these two values up after we square them and then take the square root, which gives us our C value, aka our D. So whichever way you decide to go about solving this problem, it's really good to know both methods in case you're dealing with very, very large numbers and graphing it might not be feasible. Okay, so just to reiterate, the Pythagorean theorem tells us how the lengths of three sides of right triangles relate to one another. And writing this formula during each of your practice examples, both with me as well as on your own, when you're enforcing this new knowledge, will really help you memorize the theorem, and then it will just build up your muscle memory, which will also help you memorize the Pythagorean theorem. So below here, we once again have our formal definition with a very straightforward illustration. And then we finally arrive at a nice example 5 utilizing this Pythagorean theorem. So we just want to find the length of the other leg. And so if we're given one leg is 12, the hypotenuse is 13, that third leg will represent that as x or as a, and then we can plug it in. So we have x squared plus 12 squared is equal to 13 squared. 12 squared is 144. 13 squared is 169. Utilize your inverse operations and subtract 144 from both sides. 169 minus 144 is 25. And then let's go ahead and take the square root of both sides so that we can get that a value to be of length 5, which is the length of that second leg. And we are done. So this concludes our section 2.3. Let me know if you have any questions. And next time we will be going over our, perfect timing, we'll be going over our section 2.5. All right, take care, everyone.